Welcome, cosmic explorers, science students, and astronomy buffs, to a journey into the most enigmatic corners of our solar system. Have you ever truly considered Mercury, the tiny, scorching world closest to our Sun? Often overlooked, this planet is far from a static, barren rock. Prepare to have your perceptions shattered, because Mercury harbors a shocking secret. It's still actively shrinking. And that's just the beginning of its profound mysteries. What if we told you this diminutive world might also conceal a colossal layer of diamonds beneath its surface? Join us as we unravel the scientific marvels of Mercury. For decades, the prevailing scientific consensus painted Mercury as a geologically inert body, much like our moon. It was believed to be a heavily cratered, ancient world, its evolutionary processes long concluded. This view suggested a planet that had cooled and solidified eons ago, leaving behind a static, unchanging landscape. However, the universe, in its infinite wisdom, often delights in defying our expectations. Recent groundbreaking discoveries have dramatically overturned this long-held belief. Mercury, it turns out, is a surprisingly dynamic and tectonically active planet. Far from being a frozen relic, it continues to undergo significant geological changes even today. Imagine a cosmic prune, but one that is actively contracting, reshaping its very crust. This ongoing process makes Mercury a living laboratory for planetary evolution, offering insights into the forces that sculpt worlds. How did we arrive at this astonishing conclusion? The scientific journey began with our initial robotic emissaries. Our first intimate glimpse of Mercury came courtesy of NASA's Mariner 10 spacecraft in the mid-1970s. This pioneering mission provided tantalizing images of a heavily cratered surface, punctuated by peculiar, cliff-like features. These geological formations, known as lobate scarps, immediately piqued the interest of planetary geologists. Scientists hypothesized that these scarps were indeed wrinkles, direct evidence of the planet contracting as its interior cooled. However, Mariner 10 only managed to map less than half of Mercury's surface. This limited coverage meant that the idea of a shrinking Mercury remained largely a compelling hypothesis, awaiting further empirical validation. The scientific community needed more data, a more comprehensive view, to confirm this intriguing theory. Then came the true game changer: NASA's Messenger spacecraft, launched in 2004. Messenger, Mercury surface, space environment, geochemistry, and ranging embarked on an ambitious mission to orbit Mercury. From 2011 to 2015, this remarkable probe provided unprecedented, almost global coverage of the planet's enigmatic surface. The data Messenger transmitted back to Earth was nothing short of mind-blowing, fundamentally altering our understanding of Mercury. What Messenger revealed was a vast network of thousands of tiny, fresh-looking fault scarps. These features were distributed across the entire planet, not just in isolated regions. Crucially, their pristine appearance indicated they were geologically young, not ancient scars from billions of years ago. This was undeniable empirical proof that Mercury is still actively shrinking in the present epoch. It was akin to finding fresh footprints in the cosmic dust, irrefutable evidence of ongoing geological activity. Messenger's detailed mapping allowed scientists to quantify the extent of this contraction. The data indicated that Mercury has shrunk significantly more than previously estimated. Its radius has decreased by as much as 7 kilometers, approximately 4.3 miles, over its history. To put that into perspective, this is equivalent to shedding a layer of its outer crust thicker than the Grand Canyon is deep. This substantial reduction in size underscores the immense internal forces at play within this small world. So what precisely drives this planetary contraction? The answer lies deep within Mercury's interior, specifically its extraordinary core. This little planet possesses a core that is proportionally immense, far larger relative to its overall size than Earth's core. Imagine a celestial body that is in essence mostly a giant metallic sphere. This unique internal structure is key to understanding its ongoing geological activity. Mercury's core is not a simple, uniform entity. Scientific models supported by Messenger data suggest a complex, layered structure. It is believed to consist of a solid inner core, enveloped by a liquid outer core, and potentially even a solid outer layer of iron sulfide. This intricate composition plays a critical role in the planet's thermal evolution. Here's the scientific kicker. This super-hot, predominantly iron core is slowly, inexorably cooling down. As the molten iron within the liquid outer core gradually solidifies and crystallizes onto the solid inner core, it undergoes a phase change. This solidification process causes the material to decrease in volume. This volumetric shrinkage of the core exerts a powerful gravitational pull on the planet's overlying layers. As the core contracts, it effectively pulls the planet's outer layers inward. This immense compressive stress causes the rigid crust to buckle, fold, and crack. These geological deformations manifest as the distinctive scarps and ridges that messengers so meticulously mapped. It's a fascinating process, akin to a giant, cooling metallic sphere wrinkling its skin as it shrinks. This mechanism, known as global contraction, is a fundamental process in the thermal evolution of rocky planets. Now, a natural question arises for any budding geologist or planetary scientist. Earth also has a core, and it exhibits significant tectonic activity. How is Mercury different? This is an excellent point, highlighting a crucial distinction in planetary dynamics. While both planets are tectonically active, the mechanisms driving their surface changes are fundamentally different. Earth is characterized by plate tectonics. Its lithosphere, the rigid outer shell, is broken into several large plates that constantly move, collide, and slide past one another. This dynamic process is responsible for earthquakes, volcanic activity, and the formation of mountain ranges. It's a system driven by convection currents within Earth's mantle, recycling crustal material over geological timescales. Mercury, on the other hand, is often referred to as a one-plate planet. Its lithosphere is thought to be a single, continuous shell, not fragmented into moving plates. Therefore, its shrinking is a more global, uniform squeeze applied across its entire crust. This pervasive compression leads to the formation of those unique wrinkle ridges and lobate scarps, which are distinct from the fault lines and subduction zones seen on Earth. This contrast provides invaluable insights into the diverse pathways of planetary evolution, demonstrating that tectonic activity can manifest in multiple forms depending on a planet's internal structure and thermal history. But wait, the scientific intrigue surrounding Mercury deepens. Despite its diminutive size and rapid cooling, Mercury possesses its own intrinsic magnetic field. This discovery was a monumental surprise to the scientific community. Prior to its detection, many planetary scientists theorized that Mercury's core would have completely solidified by now, effectively killing any magnetic dynamo. A dynamo, the mechanism that generates magnetic fields in planets, typically requires a large, rotating body of electrically conducting liquid metal. Yet, Mercury's magnetic field is undeniably present. It is significantly weaker than Earth's, roughly 100 times less intense. Furthermore, it exhibits peculiar characteristics. It is highly tilted relative to the planet's rotational axis, dynamic and notably asymmetrical. It's like a cosmic compass that can't quite make up its mind, constantly shifting and fluctuating. This anomalous magnetic field challenges our understanding of planetary dynamos. The existence of this field strongly suggests that Mercury still retains a partially liquid outer core. The precise mechanism generating this weak, peculiar field is still a subject of intense scientific debate and ongoing research. Some theories propose a fossil field, a remnant from an earlier, stronger dynamo. Others suggest a unique, shallow dynamo operating within a thin, liquid layer of the outer core. Regardless of the exact mechanism, Mercury's magnetic field provides a unique natural laboratory for studying planetary magnetism under extreme conditions, offering clues that could refine our models of Earth's own geodynamo. And now, for perhaps the most astonishing and fascinating hypothesis concerning Mercury. Recent research suggests this planet might be hiding a massive hidden layer of diamonds beneath its crust. Yes, you heard that correctly. Diamonds, the very same precious gems we covet on Earth. This isn't merely a fanciful notion. It's a scientifically plausible theory rooted in Mercury's unique composition and formation history. The scientific basis for this dazzling idea lies in Mercury's primordial composition. Models of early solar system formation indicate that Mercury accreted from a region of the protoplanetary disk that was exceptionally rich in carbon. This means Mercury has a significantly higher abundance of carbon than Earth. This carbon would have been incorporated into the planet's interior during its formation. Scientists hypothesize that as Mercury's liquid iron core slowly crystallized and solidified over billions of years, it would have expelled impurities. Carbon, being less soluble in solid iron than in molten iron, would have been progressively enriched in the remaining liquid melt. As this carbon-rich melt continued to cool and crystallize, under the immense pressures and temperatures deep within the planet, it could have formed diamonds. These diamonds, being less dense than the surrounding molten iron, would then have floated upwards, accumulating at the core mantle boundary. This diamond rain hypothesis could explain several puzzling aspects of Mercury. For instance, it might account for Mercury's unusually dark surface. If carbon-rich material, including diamonds, was brought to the surface through ancient volcanic activity, it could contribute to the planet's low albedo. It might also explain why Mercury's volcanic activity appears to have ceased relatively early in its history. A diamond-rich mantle could have different rheological properties, affecting magma generation and ascent. Imagine a planet with a diamond heart, a truly breathtaking concept that pushes the boundaries of our understanding of planetary interiors. The mysteries of Mercury continue to beckon, inspiring the next generation of planetary missions. The European Space Agency, ESA, and Japan's Aerospace Exploration Agency, JAXA, have teamed up on the ambitious Bepi-Colombo mission. This sophisticated spacecraft, launched in 2018, is currently on a complex, multi-year journey to Mercury, utilizing numerous planetary flybys to gradually slow down and enter orbit. Bepi-Colombo is not just one orbiter, but two: ESA's Mercury Planetary Orbiter, MPO, and JAXA's Mercury Magnetospheric Orbiter, MMO, also known as MEO. When these two orbiters finally begin their scientific operations around Mercury in 2025, they are poised to revolutionize our understanding of this incredible world. The MPO will focus on mapping Mercury's surface, studying its composition, and analyzing its exosphere. The MMO will delve into the planet's magnetic field and its interaction with the solar wind, providing unprecedented data on its anomalous magnetosphere. The data from Bepi-Colombo will allow scientists to test the diamond hypothesis, refine models of Mercury's core and its shrinking process, and gain deeper insights into the origin and evolution of its magnetic field. This mission represents a monumental leap in our ability to study the innermost planet, promising to unlock even more of its dazzling secrets. So, Mercury, once dismissed as a boring dead rock, has unequivocally proven itself to be a tiny titan of tectonics, brimming with scientific surprises. Its ongoing contraction, its peculiar and dynamic magnetic field, and the mind-boggling possibility of a diamond-rich mantle challenge everything we thought we knew about the evolution of small, rocky planets. Mercury isn't merely a planet. It's a cosmic laboratory, offering invaluable lessons about how rocky worlds form, how their interiors evolve, and even how they generate their own protective magnetic fields. It serves as a powerful reminder that even the smallest celestial bodies can harbor the biggest, most dazzling, and scientifically profound secrets. This fascinating world continues to teach us that planetary evolution is a far more diverse and complex process than we once imagined. From its shrinking crust to its enigmatic core and potential diamond riches, Mercury stands as a testament to the endless wonders awaiting discovery in our own cosmic backyard. What do you find most intriguing about Mercury's incredible secrets? Do you believe in the diamond planet hypothesis? Share your thoughts and questions in the comments section below. If you've enjoyed this deep dive into Mercury's scientific marvels, please hit that like button. Subscribe to our channel for more mind-blowing space facts and scientific explorations, and ring that notification bell so you don't miss our next adventure into the cosmos. Join our community of space enthusiasts and science students as we continue to explore the universe, one fascinating discovery at a time.